Okay, welcome to the third example in the chapter of torsion. The question reads, the A36 steel shaft has a diameter of 60 millimeters and it is fixed at its ends A and B. If it is subjected to the torque shown, determine the absolute maximum shear stress in the shaft. Okay, so we can put down our givens, right? So number one, givens. First thing that I recall is that the diameter of the shaft is 60 millimeters. We have a fixed connection, so fixed at A and B. What else can we say? Well, we know that it's A36 steel, right? So automatically by now you should know that that is 200 gigapascals. However, in this, this is one of those statically indeterminate like angle of rotation problems, right? So we're going to introduce a new formula in givens before I say the next thing. So this is your angle of rotation. It is equal to the torque that acts at, and this is the angle of like deformation, right? I want to see how much, by what angle, my cross section has deformed by, right? It's kind of hard to see with the exact same color, but hopefully it's like basic. Fine, I'll draw it. Something like this. Amazing. Something. Okay, this is actually incredible. This is my original circle, right? If this is my other circle, just a little bit over the top. Let's say my original circle has a radius like this. This one is rotated like so, right? By this angle theta in radians. As simple as that, right? It's literally the angle of deformation. Obviously, even this is exaggerated. We'll have like very, very small values, but that is the idea. So hopefully you get it. This is basically like a deformation, but in angle form. Okay, or it is a deformation in angle form. Okay, so my angle of deformation in radians, remember that. You deserve to get it wrong if you put it in degrees, to be honest. But this is equal to my torque, right, multiplied by the length of my shaft, right, or the length, basically of my shaft, and I'll explain that a bit later as well, divided by my polar moment of inertia, multiplied by my shear modulus, right, my modulus of rigidity. And for A36 steel, my modulus of rigidity is a value of 80 gigapascals, or 80,000 megapascals. Okay, perfect. I think we could put one more formula in here, which is shear stress in for torsional loading is equal to the torque multiplied by distance c divided by, where in this example, since we have a solid shaft, it represents the radius, divided by our polar moment of inertia. Okay, we can continue. Basically, we want to find the maximum shear stress developed in our shaft. So to do that, so let's first write it down. So unknowns. To find the maximum shear stress developed in our shaft, so tau max, we need to find the maximum torque in our shaft, right? So that's step one, because it's simply just using this formula. We have J, we have C, right? J for this scenario is pi over 2 r to the cubed, right? We have to find the maximum torque. That's all we have to do. So that is our next course of action. So number 3, we want to find max torque, right? So find max torque. Okay, how are we going to do that? Well, we're just going to sum torques like how we always have for a while now, right? So let's just draw our shaft like so. We're not going to cut anything just yet, right? So it kind of looks like that, and then dot, 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 right? If I look at my diagram, it looks like here at point C, this is point C, this is point D, this is point B, this is point A, right? At C, I have a torque of 500 newton meters. At D, I have a clockwise torque of 200 newton meters. And then remember, I have a fixed connection at A and B. So I'm going to assume that I have a clockwise torque, TB, at this wall, and a clockwise torque, or my bad, a counterclockwise torque at A, at this wall, so TA, right? So I will draw that as well. So we can call this TA, right? And then this is TB, and I assume them to be positive. If I sum my torques, I say counterclockwise is positive, right? What am I going to be left with? I'm going to say that TA, or I'm going to be left with TA minus 500 newton meters, because it's clockwise, minus 200 newton meters, plus TB, right? So from this, I'm going to get an expression, which is namely TA plus TB. So my torque at my wall A and my torque at my wall B is equal to a value of 700 Newton meters. Beautiful stuff, but not that beautiful just yet. Why is that? Well, again, and if I call this my equation 1, if you think back to axial deformation and axial loadings, we have a statically indeterminate problem, right? We have two unknowns in one equation, right? Why do we even need to find TA and TB? We want to find the maximum torque. Well, you don't exactly know if the maximum torque is 500, right? What if TA is 700, right? Or what if TB is, I don't know, 900, right? They could easily be, I don't know, 100 or something like that. But we have to at least check just in case, right? To see the maximum torque. Okay, and even later, we'll get to it later. But anyway, we need to find these two unknowns. But we only have one equation. We need another linearly independent equation to solve for our unknowns. And how we're going to do that is we're going to use deformation analysis, right? So deformation analysis. It's a statically indeterminate problem. Deformation analysis. Beautiful stuff. Okay, so to do this, we have to come up with a scenario that basically allows us to relate this formula for different points on our shaft, right? Okay. With angles, it's a bit, let me just go through the explanation, then if anything pops up, I'll explain it. Let's say, for example, let's assume, again, we have this 200 Newton meter, right? Torque. We have this 500 Newton meter torque. We have this TA, as we've established. Let's assume B is stationary, right? We don't have, like, we're taking the, we're basically analyzing the deformation caused by this 200. The deformation, it's not stationary, but like, in terms of B, we're going to keep it fixed. We're going to assume B is fixed. Assume B is fixed. And what this allows us to do, it's not actually fixed, or it is fixed, but basically, the core concept of this is we need a reference point, right? Because if we allow all four of them to rotate, where are we going to take our reference? What's going to be our reference? If we have B as our reference point, then I'm going to find the angle of rotation caused by this 200 Newton meter torque relative to B. I'm going to find this angle of rotation due to the 500 Newton meter torque relative to B. And then I'm going to find the angle of deformation due to TA, right? Relative to B. Right, so they're all going to be relative to B. And basically what that means is, let's pretend this wall is fixed, right? Pretend this one doesn't move. And then this one will move, and this one will move, and then this one will move, right? So let's kind of draw that out. So hopefully this drawing will make a bit more sense. So basically I have A, like so. And we're going to assume B is fixed. Assume B fixed. So I'm just looking at the deformation angle relative to B. So I have like a starting point. If I zoom out a bit, 1 meter away, 1.5 meters away, 1 meter away. I know it's not the scale, forgive me. This is A, C, D. This is 1, 1.5, and then 1 as well. Here I have a clockwise TA, counterclockwise 500. My bad. This is counterclockwise. This is clockwise. And then this is also a clockwise 200 Newton meters. Beautiful stuff. Now I'm going to calculate or I'm going to come up with a formula that relates the angles of deformation. So what's happening in this specific scenario? Well, I'm going to have an angle of deformation caused by the 200 Newton meter torque, an angle of deformation caused by the 500 Newton meter torque, and an angle of deformation caused by my torque TA. Okay, how can I come up with an expression? Well, let's say, for example, just an example, let's screw this one off for now. Let's say that these two torques right here cause an angle deformation of, I don't know, I'll exaggerate, let's say 30 degrees. And let's not put degrees. Let's do pi over, what is 30 degrees? Pi over 6, right? Pi over 6, right? It causes an angle of deformation of pi over 6, right? So now my shaft has rotated by a value, by an angle of pi over 6, right? Clockwise. I'm gonna look back at my shaft, pi over 6. I'm gonna look back at my shaft. Is it actually rotated pi over 6 clockwise? Well, no. It's at the 0 position, right? So what's gonna rotate it back? Well, the thing that's gonna rotate it back is this counterclockwise deformation caused by my torque TA, right? So if due to theta 200 plus theta 500, my shaft has rotated about the torsional axis by a value of pi over 6, well, it's going to rotate back to position due to theta TA by, again, a value of pi over 6. What does this mean? Well, this means that I can come up with the expression that, this is clockwise, this is counterclockwise, I can come up with the expression that theta 200, the deformation caused by the 200 Newton meter torque, plus the deformation caused by the 500 Newton meter torque is equal to the deformation caused by my torque TA. And just like that, I have found a linearly independent equation that eventually will allow me to calculate, in this case, TA. Right? So just like that, we found that equation. Hopefully that kind of explanation was useful. Okay, so we're gonna say the equation that we just derived, 500, right? We're gonna use this equation. So TA, right? And I'll put it over here. Theta is equal to TL over J, or GJ. JG. Okay, it doesn't really matter. JG. Okay, so it's TL. What's my length for this torque A? Well, it's 1 relative to B. It's 1 plus 1.5 plus 1. So that's 3.5, right? Multiplied by 3.5 meters. Divided by JG. I'll just keep it like that for now. And you'll see in a second. Okay, my torque for this 200 Newton meter deformation. Well, that's just simply 200 Newton meters, right? At a distance of 1 meter, right? Divided by JG plus 500 Newton meters at a distance of 2.5 meters divided by JG. Since I have the same constant material, A36 steel, I don't even need to put, and they have the same polar moment of inertia, they all act at the same constant diameter shaft. If, for example, for some reason the shaft got bigger, for example, we can't cancel this out, right? Or if, I don't know, you had a different material for some reason on this part of the shaft. Obviously, you can't do things like this, so please take note of that. But long story short, these cancel out. And from this, you can easily find that your TA value, your torque at TA, is equal to 414.286 Newton meters from doing this lovely isolation. And then by plugging, and let's call this formula 2, by the way, so we're keeping track, 2. By plugging this value into your equation 1, so plug in 1, you're going to end up getting that TB is equal to 285.71 Newton meters. Okay, beautiful. And just like that, you found your TA and your TB. Beautiful stuff. Okay, the question is, we go back to what we said before. Is this higher than is this the maximum torque that acts in my shaft? Is this the maximum torque that acts in my shaft? Is the 500 the maximum torque that acts in my shaft? Well, this is kind of like an illusion, kind of. This is an external torque. I want to see the internal torque. I want to see the torque throughout my shaft, and the only way to do that is simply like what we did in the last two examples, cutting the beam open. So if like that explanation doesn't make sense, just watch and you'll remember. Okay, so max shear stress. We want to find the max shear stress, but before that, we're going to find the max torque. And how we do that, basically, using a lovely torque plot, right? So if we draw our beam like so, again, just as a reference, right? We have TA clockwise, we have 500 Newton meters, we have 200 Newton meters, and we have TB, right? And we have values for all of them right now. What I'm going to do is I'm going to draw a torque plot. Basically, I'm going to start from here and then move my way through the beam, or through the shaft. So plus X in meters, plus torque, right, in Newton meters. I start at counterclockwise. Let's say counterclockwise is positive. I'm going to start at counterclockwise, right? A value of, what is my TA? Well, it's simply 414.286 Newton meters, right? Okay, beautiful. If I cut my beam from this section, and let's draw the points as well. This is A. This is, I forgot, C, D, B, right? So C, D, and B, right? If I cut my beam right here, I take sum of torques, right, just on this small section. The only torque that's acting, TA, is the reactionary torque that I have from section A to C, right? So therefore, the only torque that I have from A to C is this TA, right? So it's a constant function as we move through the beam, right? Until we reach 1 meter, I suppose, right? If this is 1, this is 1.5, and this is 1. Until we reach 1 meter, 1, we have this constant torque, right? Okay, now I cut my beam between C and D. What happens? TA, 500. I cut, right? If I take summation of torque, right, I'm going to end up getting a value of negative 85.714 as my reactionary torque, right? As my reactionary torque, because it's clockwise, right? And this makes sense because it's just 500, or it's actually 414.286 minus 500, right? So I'm going to get this value. So again, I'm going to plug that in. So it might be around here. So minus 85.714. And then it's going to be constant from C all the way to D. So from 1 all the way to 2.5. And then I end here again. 2.5 meters, right? And this is basically what we're doing is we're finding the internal torque, right? The torque that our shaft actually endures, okay? And last but not least, between D and B, I need to cut, right? And I take summation of torques for this section. If I quickly draw it, TA, 500, 200, and then I take summation of torque, assume it to be positive, at my cut, right? If I take summation of torque at my cut, I'm going to end up getting a value of negative 285.714. And just to make sure that this like really like makes sense, let's say that like if I just, this is like conceptually kind of, if I look at my beam from the top, right? If I look at it from the top, my beam kind of looks like a bar, right? Kind of looks like a bar, right? And if this is my cut, actually, let me make this disappear for a second. If this is my beam, right, and I look at it from the top, if this is my cut, then the reactionary torque that happens on this side must happen equal and opposite on this side, right? Hopefully that's correct, right? What did we just say? We said that if we look at this portion right here, right, and we find the torque at this cut, it's going to be, I think we got a negative, so it's actually going to be clockwise, and it's going to have a magnitude of, namely negative, 285.714. If I look at the other side, what's the other side? The other side is just this little portion remaining over here, right? If I take the summation just of this little side, right, and I'm looking at it like that, right, and I cut it, right, so this is my point B, and this is my point D, the only torque that I have acting is, hopefully I'm right, it's a counterclockwise, right? So it's counterclockwise, TB. So if I take my section, right, it's simply going to be that my torque at my section is going to equal positive 285.714, right, TB. So see how it works out beautifully, right? So even if you did go from this side to this side, you would still get the same answer, right? So it just works out beautifully. But long story short, for this side, we have negative all the way to 3.5 meters. We have 3.5 meters. We have a value of negative 285.71 meters, and this represents the torque versus my distance x if I started at A, right? But I could have easily, again, started at B and went to A. Okay, what do we get from this? We get that the maximum torque in our shaft, endured by our shaft, is not 500, but it's actually 4.286. So therefore, max torque is 414.286 Newton meters. Therefore, I can plug that into my shear stress equation. So tau max is equal to the maximum torque. So max C over J. I get the tau max. Oh my God, that is atrocious. I need to zoom in to write properly. Tau max is equal to 414.286 Newton meters multiplied by C, which I think it's 30, but we'll check in a second, which is our radius, right? And pi over 2, radius squared, 30 millimeters, no, not squared, to the fourth. And I'm going to get a tau max value. The maximum shear stress endured by a shaft is going to be 9.8, don't forget the units, 9.8768 megapascals, and that is your final answer. If we simply just check the diameter, 60, so radius is 30. Okay, that is the answer to this question.